Okay, let's get started. Want to start by talking about the homework, which is based on this data for vetoes. So starting off with the papers that you all read. So how many of y'all read a paper where they did some sort of quantitative analysis of like vetoes or overrides or something? So most of those are going to be quantitative, or at least you can find one that is. Of course, you know, back in the 1960s and stuff like that, they would probably, there's entire books about it, where they would just sort of lay out the history of what happened with the bill and, you know, different theories about what is this. Okay. So of those who got to read a paper that at least used some quantitative methods, how many of those had any explicit Bayesian content at all? Zero. Not a real surprise. As we've seen on the first day, political science literature, Bayesian methods make up extraordinarily small fraction of less than 1% of total articles published in political science journals. But how many of those had some implicit Bayesian thinking, even if they didn't use MCMC methods? So you want to describe what you saw with the sort of implicit Bayesian?
Yeah, so the article that I looked at was basically trying to factor in like individual and institutional factors and how that might influence like a president's motivation in doing a veto. So they took like subset of data from like different years or congressional sessions, and they were basically like trying to see how these different variables kind of shape whether a president would or would not veto a specific bill using like logistical regression. But I thought there were some implicit Bayesian methods just because they're looking at, there's like a lot of like uncertainty when it comes to like, you know, dealing with like major historical events or just presidential popularity, or even like unemployment rate was another one.
Did you want to say something?
Yeah, the one that I read was discussing how it's like commonly done, and that obviously is a frequentist method, like using maximum likelihood and everything. But the authors suggested using King's like GEC method and showed like why that's better to model it. And they talked about how that, like in that paper, they were like kind of updating the field's view on what should be the best method. So I took it as like they are, even though what they're using is a frequentist method, they're presenting evidence to the field to like change how something is done.
Yeah, I think that if that's what we mean by Bayesian, like trying to convince someone to change their beliefs about something, then like almost all published papers would be Bayesian in that sense. So even though I guess all the quantitative papers were ultimately using a frequentist method, obtaining point estimates, probably doing null hypothesis tests, all those sorts of things like that, how many of the papers that you read had any sort of discussion or acknowledgement that these data are not a random sample of vetoes? Yes or no?
Yes.
It had some?
Yeah.
That was one more than I was expecting. Okay. What did they say?
Yeah, for mine it was basically they were trying to pick bills that were like, I forgot what it was called, but it was basically like if it would have a chance of being vetoed, but then they did like a second round of like kind of sampling to see whether if they missed any other bills that were kind of under that same camp. So there was a little bit of, I don't want to call it randomized sampling, but they were trying to do like couple rounds of finding those bills that were more prone to being vetoed.
So selection of bills.
Yeah.
But the bills themselves are not randomized.
They're not, no.
We have not yet evolved to the point where bills are written by, you know, ChatGPT stringing together a random set of words or anything like that. So the senators and the congressional representatives, who they are is not randomized. The bills they write are not randomized. The bills they pass are not a random subset of the bills that are under consideration. Which bills get vetoed is not random. Which bills get none of this is random. Moreover, I mean, people will say, well, there's going to be more vetoes in the future. So just because we have literally every single veto that there has been since the 1700s in this data set doesn't mean we have all possible vetoes. But that doesn't mean the past is a random sample of all time. What the frequentist view of probability is the proportion of times that something happens as the number of randomizations goes to infinity. If nothing is being randomized, then you don't have frequentist probability. So I think the main thing that I would say, like, yes, the frequentist interpretation of probability is not as good as the Bayesian interpretation of probability. But you can make a case for the frequentist stuff, and Fisher did. And so that gets into a rabbit hole of kind of a complicated or, detailed set of arguments. And people like McElreath just, don't want to get into any of that anymore. But I would say the main thing is that the frequentist conception of probability just isn't applicable to that much in social science. Now, it's used all the time despite it not being applicable. But once you sort of get back to the idea of what's the frequentist interpretation of probability and does it apply to vetoes or anything historical, anything having to do with institutions, anything having to do with politicians, anything having to do with macroeconomic history or a lot of the stuff in sociology and psychology too, and it's just not very much. But, maximum likelihood, other frequentist estimators are used all the time, and that creates some, dissonance, or it should. It doesn't really create that much dissonance on the part of most people who practice social science. But once you see it that way, it's easier to recognize that what is going on in the social science literature is a bunch of people who don't know this stuff that well, like they took a class or two when they were in graduate school, and it's a lot of convention rather than anything that has a real solid basis in probability or quantitative methodology, and it's a lot of people imitating a lot of other people, none of whom is, really even making the case for why they do what they do. And so, there's lots of papers that you could read. I got this older one, which is rather famous, which was by Gary King, and it was primarily a methodological paper intended to introduce this new-ish, certainly new at the time, probability distribution known as the generalized event count distribution, whose probability mass function has this somewhat complicated form, but it can and has been implemented, not in Stan, but it could be done in the event. This generalized event count distribution can be used for count outcomes, which are fairly common in the social science, estimating the sigma squared parameter, which is not the variance, but has the property that if sigma squared is 1, this simplifies to a Poisson. Sigma squared is greater than 1, it specializes to negative binomial. And if sigma squared is less than 1, it has to be greater than 0. But if it's less than 1, then it specializes to a count model that has under dispersion, less dispersion than a Poisson does. And these sorts of efforts are good. If you can take essentially 3 different cases, Poisson, negative binomial, and the opposite of negative binomial that has under dispersion, and combine them into one even more general distribution that you can estimate a continuous parameter such as sigma squared, then you don't have to take a position in advance as to whether there's going to be over dispersion or under dispersion. Poisson is a special case where it crosses over that. So all those things are, good. And then Gary applies this to veto challenges, so that's a little bit different. Whether there's a vote to overturn a veto rather than is it successful or not or anything like that. And so that's going to include some fairly, standard predictors. He includes the number of bills that were vetoed, so that's kind of like an offset, except he estimates the coefficient rather than fixing it to 1. But since this was 1989, no surprise at all, use maximum likelihood estimation rather than Bayesian estimation. But given that it's Gary, no surprise at all that he would continue to use maximum likelihood estimation even after Bayesian methods, MCMC and whatnot, came into focus, or at least in the applied statistics literature. But anytime you read something of Gary King's, it's a bit of a challenge because it kind of seems like on some days he's Bayesian and some days he's frequentist. But on most of the days when he talks about using maximum likelihood estimator, he's talking about essentially using it as a Bayesian estimator. Basically, kind of like what we saw with the global warming thing. Assume the posterior distribution is normal, in which case the maximum likelihood estimates are the expectation of that assumed normal posterior distribution, in which case you don't need to use MCMC, you can just use optimization to find it. And to the extent that is a reasonable approximation, it's only a reasonable approximation under improper priors on the parameters, which, that paper that we did the homework talked about why that is not ideal, but essentially, okay, you have an approximation, maybe there's an asymptotic case to be made for it, but using maximum likelihood as a Bayesian estimator is always worse than using a Bayesian estimator as a Bayesian estimator, as opposed to using maximum likelihood, which Fisher created to prevent Bayesian estimation from taking hold in science in the 1920s. And so that fairly common, maybe it's explicit, oftentimes implicit, usage of frequentist estimators toward Bayesian goals is actually reasonably common in the social sciences, even though Bayesian estimation techniques are not, and even though Bayesian estimation techniques would be much better for Bayesian goals than something that just produces point estimates under an unnecessary assumption that the posterior distribution is normal. So Stan doesn't assume that. And so it's adding an assumption that is not really verifiable from the approximation. So the only way you could know whether that approximation was good or bad would be to do it a genuinely Bayesian way and then compare them. But if you do it a genuinely Bayesian way, why would you need an approximation to something that you already have the genuine article? So anyway, that comes up a lot with Gary's papers, and Gary's papers have a lot of influence on the political methodology and outside politics as well. Okay, so model. There's a variety of ways you could go with this. I first created dummy variables as to whether the president's party was in the minority in the House and the Senate. And then I subtracted 50 from the percentages of each. That's essentially centering those, and then use those along with the interaction between those in a generative model. So you could construct the linear predictors in different ways. But the main idea here is that you can get a fairly rich generative model for something in the social sciences by chaining a bunch of conditional distributions together. Of course, you've got marginal distributions for the parameters. That's your priors, what you believe about them before you see a new to you set of data. And then you have, the logarithm of the expected number of regular vetoes given the predictors and the parameters. And then, you could map that to the expectation using the antilog function and, have multiplicative errors to make it negative binomial, etc. And then conditional on the number of regular vetoes, use that as the size parameter in a binomial model for the number of regular vetoes that get overridden. And you can use a similar but not necessarily exactly the same linear predictor for predicting success in overriding that uses the same logic but not necessarily exactly the same form as your linear predictor for the number of regular overrides. So the dplyr code might look a little bit like this. Draw from the priors of everything, cross-join it together, make the first linear predictor, map it to the expected count, gamma errors there, draw the number of regular vetoes from a Poisson with expectation mu multiplied by epsilon. So mu is still going to be the expectation because epsilon has an expectation of 1 and is independent of mu. But if you integrate over epsilon, then the count given mu is negative binomial, and given mu and phi. And then given this count of regular vetoes, then you can binomial with size equal regular, logit binomial model for number of those that are successfully overridden. Can look at plots to see whether you're predicting something reasonable. Not be reasonable to be predicting thousands of vetoes, or at least in the United States. That would be not something that we've ever really seen. You can also make these plots, conditional on the predictors. So here's the one for overrides. Basically, if the president's party is not in the minority in either the House or the Senate, it's going to predict, essentially guarantee, that there are no overrides, presumably because there's not many or maybe not any vetoed bills to begin with. Why would Congress be passing something that the president from their same party opposes? It's occasionally happened, but not often. Just the president's party is a minority in one of them, then slightly lower chance of having 0 vetoes, but still not that much. If the president's party is a minority in both the House and the Senate, then a lot of things can happen with small probability. That seems pretty reasonable. And having reasonable predictions is a necessary and almost sufficient condition for your priors on the parameters to be reasonable. But your priors on the parameters need to be fairly concentrated, fairly close to 0, particularly with these anti-log inverse link functions, because that can get very big very quickly if you're putting too much probability on coefficients that are too positive. We get that. Then using RStan-ARM to estimate these things. So I included the interaction between those two, prior, stuff like that. You get a lot of over-dispersion in the sense that the draws of phi tend to be small, and the negative binomial approaches the Poisson as phi goes to infinity, or at least phi is large relative to mu squared. You can also plot this by looking at the contrast between the posterior draws and the prior draws. This is what I did the video today in recitation for those of you who hadn't had a chance to see it yet, talking about how this is really a way of quantifying or visualizing the value added of a particular study. If you put priors that are reasonable to you and or reasonable to the audience, and then you update those beliefs to the posterior distribution, the influence or whatever of your efforts is reflected in how these beliefs change. In this case, not so much. So I don't know if I really added a whole lot of value above and beyond what I thought I already knew. But what I thought I already knew, I thought all scholars of American politics would already know. So maybe this wasn't the most value-added exercise, but it was good practice. So in a manner of speaking, if I came up with the conclusion, when the president's party has a lot of his friends in the House or the Senate, there's not going to be a lot of vetoes and there's going to be even fewer overrides. I don't think anyone would fall over hearing that news. But anyway. And then you can do counterfactuals. And so this illustrates something that I think is important, but I haven't maybe said yet. So this is like, okay, what if maybe a couple more people, Republicans in the House resigned and then the Democrats had a bare majority in the House? When answering substantive questions of interest, we query models rather than interpreting parameters. Now, in an extremely totally linear flat model, then those two things coincide. The implication of the model is entirely dictated by a coefficient in a linear model. But these are generalized linear models that we're talking about on this homework. There's a nonlinear, albeit increasing, inverse link function applied to the linear predictor in order to get the expected count. And those nonlinear functions are not something that can be completely described by a coefficient. Or another way of saying it, not one coefficient in isolation determines how the expectation changes. It depends on all of the predictors simultaneously. But when you do things the Bayesian way, once you get the posterior draws of the parameters of the model, you can make any database-like query to the model as a whole, rather than for one parameter in isolation of everything else. In addition, in the posterior distribution, the parameters aren't independent of each other. So we need to be constructing this thing jointly. So in this scenario where the Democrats controlled the House, then the most likely number of vetoes would be 0 with like 30% chance, and median would be 2. Seems kind of possible. Also, if we model the overrides with a binomial logit sort of model, we can, say stuff about the past that wasn't even counterfactual. This was like actually factual. After the bulk of the Iraq invasion by George W. Bush and the Democrats controlled Congress, what's the probability they would override a veto? Not that much, probably less than 10% chance. Even though they controlled both the House and the Senate, they didn't control either by all that much. It would have been a tough undertaking to get 2/3 in both the House and the Senate, because that would have required a fair number of Republicans to vote against something that George W. Bush favored. So anyway, we're querying a model rather than basing our conclusion on any one coefficient. And these plots of mu reflect all the coefficients and their uncertainty after we've conditioned the data. That's posterior stuff. So any questions about that? GLMs? Applicability to social science? Yeah.
For linear predictors in the first one, are they effectively also acting like as tuning parameters for the distribution? So that's kind of like the way I thought about it.
I tend not to use the word tuning parameters unless I'm talking about supervised learning, which I will be today, and which I have taught entire classes on in the past. The Bayes rules book does use the phrase tune the prior, which I think is a poor choice of words in that it would kind of suggest maybe, okay, you do the prior and then you come up with a posterior distribution, it doesn't really look right, and then you are like now tweaking the priors like it was a radio from 1980 or something like that, which is not what the authors of Bayes rule advocate, but you could see why someone would get confused. So if you said I'm tuning the prior predictive distribution and kind of leave it at that by choice of the prior on the parameters, I think I would be kind of okay with that, but I just avoid the word tune pretty much altogether, except in a specific context.
Tuned by acts as a shape parameter?
Yeah, I mean, they affect in a GLM, they affect the center, they affect the tails, they affect the shape, they affect everything.
Yeah.
So you need to choose them collectively so that your predictions seem respectable, before you start conditioning on the data.
Thank you.
I don't think that requires using the word tune to accomplish. Okay, so, did I already render this? Okay, 2 plus 2 is still 4, good. All right, so today we're going to be talking about model checking and comparison. This has nothing to do with model checking or comparison, but we're talking about it anyway, because it's Thursday. But before we get into that, I want to talk about some other stuff. So as I'm sure you are aware, at 8:30 a.m. today, the government announced that their estimate of the fourth quarter GDP growth in 2023 to be 3.4%, which is 0.2% higher than what it was when we did homework 2 or whatever it was. And 3.2% was 0.1% lower than what it initially estimated in like February or whatever. So it started off with an advanced estimate of 3.3, then went down to 3.2, now up to 3.4. But perhaps most equally importantly, their initial estimate of gross domestic income growth in the fourth quarter of 2023 was 4.8%. And conceptually speaking, both those are equally good estimates of our concept of economic growth after having adjusted for inflation and all that. So, under the assumptions that we were using with that homework, which were maybe a little bit stronger than what would ordinarily want to do, but we were still learning like what's a PDF at that time. If we have a normal prior on mu, conceptualizing mu as the true growth rate with expectation M, standard deviation S, using a normal likelihood for both GDP growth and GDI growth, that conditions on the unknown mu that we're trying to estimate. And this is where we made kind of a strong assumption that sigma was 0.7, exactly based on pre-pandemic data. That just made things a little bit easier at the time. Doesn't have to be does not have to be the case that you assume sigma is known. But if you do, then the posterior distribution for mu remains in the normal family. So this is an example of conjugacy between the normal prior and the normal likelihood such that the posterior distribution comes out to be normal with expectation given by this and standard deviation given by that. It's a combination of P and I and M and S and sigma and all these sorts of things. So we can see by looking at this expression in this case, because we can do it explicitly, that the recommendation in that article we read for the homework to average GDP growth and GDI growth together to get what they call GDO, or gross domestic output growth, corresponds to this posterior distribution if we let S go to infinity. So that becomes 0, that becomes 0, the sigma squareds cancel out over here, and you get P plus I over 2, which is the average that constitutes GDO. But that is a ridiculous prior distribution for someone who purports to be enough of an expert on macroeconomics to, like, why should we listen to someone who's essentially saying, I have no idea what economic growth is in the fourth quarter of 2023. I don't even know that it's almost always between -5 and 5. I'm putting infinite variance into the prior. That just means you don't know what you're talking about. So why should anyone listen to you? Certainly, predictors who are forecasting this in January or whatever had finite variance to their forecasting. If you use Ogun's law or something to, predict what, or to specify what M should be as a function of the unemployment rate change, then again, you're going to get something with a rather small variance, not an infinite variance. So you'll hear a lot, well, if you get a whole bunch of different point estimates, you should average them together. And in a manner of speaking, that is a step forward, and that an average of 2 or more things is better than any one of them individually in expectation. So you'll hear this with polls or whatever as well, like, don't pay too much attention to any particular poll, you should average a bunch of polls together. That gives you a better sense of where the candidates stand, that sort of thing. But that's also kind of just giving up. It's like, I don't know what to do, so just average them. And, you'll hear a lot people say stuff like, oh, well, I'm getting conflicting information here. Like, on one hand, the government is saying it's 3.4%. On the other hand, they're saying 4.8, which is I don't know what to do. Well, Bayesians have known what to do since the 1700s. You use Bayes' rule to reconcile conflicting information in the data and conflicts between the data and what you believed before you saw the data. In this case, we can do it with conjugacy, but it remains true if we do it with draws, as we saw on the homework. So this idea that, or this fairly frequent occurrence of people being like stumped when they get conflicting information, not knowing what to do, not knowing the fact that we have something that is intended to reconcile conflicting information into one probability distribution that reflects your beliefs about that and takes into account the fact that P and I and M were not all the same numbers. Even worse, perhaps, if P and I happen to be the same number, that doesn't mean that's the truth. They could both be off by the same error in the same direction. I mean, their standard deviation given mu is still 0.7. So you could deceive yourself into thinking, oh, well, if P and I are very similar, then that's probably right. But that doesn't rule out the fact or the possibility that they're both wrong in the same direction by the same amount this quarter. So you still need Bayes' rule to reconcile all that even if P and I were the same. So that's just kind of circling back to that. Again, you know, if we relaxed all this, we could come up with a better model. We'd have to do it all with draws, but that would be fine. Still using Bayes' rule to reconcile all this stuff. So questions about that? All right. So the first quarter is pretty much ending today. Like tomorrow and the weekend doesn't really count. So how would you go about forming a prior for mu in the first quarter of 2024? Let's say normal, why not? What sort of a normal prior would you put on mu for first quarter of this year? Which is ending in like 4 hours.
I was thinking like, because we kind of have seen the numbers for January, February, and March, like maybe do somewhere in between them for like the mean and the standard deviation, we can kind of keep it low.
Yeah, so we have some data that comes out monthly, or even weekly, or even like daily in some cases. But the main one would be unemployment changes, which comes monthly and doesn't really get revised that much. So unemployment rate has increased slightly over the first quarter. So that would maybe suggest an M that is a little bit below typical. Sure. Could certainly have a finite S.
Yeah.
Very finite S. But we might want to take into account that our posterior distribution for the fourth quarter of 2023, which was the immediately preceding quarter to this one, was historically tremendously good for the United States. Like between 2 and 3 would be typical for the United States or Western Europe, Japan, stuff like that. So to be 4-ish, you know, is almost double what it was. Moreover, the third quarter of 2023, they revised it to be 4.9. Also, not unprecedented, but extraordinarily rare to get that. So the fact that the past 2 quarters have been extremely good would maybe cause you to up your prior a bit on first quarter of 2024. That might cause you to adjust your predictions for the percentage that Biden will get in November based on the fair thing we did on the midterm. So it's all about, you know, updating and using probability, substituting a known probability distribution for any scalar or vector, but let's just say scalar for now, that you don't know. And carrying through the simulations, you know, every time you do a draw, then pretend that's the truth and just do whatever you were going to do if you knew the truth. But because you're doing it like 4,000, 10,000 times, whatever, you're going to get a distribution that reflects your uncertainty. So you just sort of carry on with the math. And one of the most important things that you can do with the math is update your distributions as new information comes in. So new personal consumption, whatever PCE stands for, it's a measure of inflation. That's happening tomorrow, 8:30. Wake up early. So you can update what you think the real growth rate for the first quarter is based on the inflation in March. That sort of thing. Questions?
Actually, kind of a slight question. So you had mentioned like unemployment. So if you were to define the model, like that would kind of be like its own variable then with this specific example, right? So that would have its own like basically.
Yeah, so I might let M be a function of, among other things, the change in unemployment rate. That would be my Okun's law. And then you would need a prior on the intercept and the coefficient and the error standard deviation for that Okun's law piece. But it would just be like we were doing on this homework, chaining conditional distributions together. So you have economic growth conditioned on change in unemployment rate, and then you have the estimated P and the I conditional on the true economic growth, and then you have the Biden success conditional on the new. Anyway, so putting all these conditional distributions together in a row, you can imply fairly rich marginal distribution for whatever's at the end of your stack of conditional distributions. Other questions about that? Okay. Also, before we get going with this model checking and prediction stuff, I believe Sebastian had some thoughts he wanted to share on a conference he attended on Friday.
Okay, so Friday was the political analytics seminar where Becca Siegel, that is the the senior data analyst of Biden campaign.
Very senior.
Very senior. Okay, director of the data science or data analytics. So she showed us like the different posterior distribution from different states, particularly like the most important states like swing states and the more like blue or red states. And there she showed us each like posterior prediction from each state and how that piece of data was used to making decisions on the campaign.
Using decision theory?
Yeah,
where the
particularly.
utility function is, do they win or does Biden
Yeah.
win the electoral college?
And where to like put more money or not to win the electoral college. And there's like this particular, these three particular states that are Michigan. No, it was Wisconsin, if I recall.
It's a state.
No, yeah, but it's Wisconsin with the like the flag.
The one with the most uncertainty
Yeah.
about it? Yeah.
So Wisconsin was this state with most uncertainty within all these like swing states, and there's also how the Georgia is I know if I recall.
So Georgia is another state?
Yeah, but it
with
was
more certainty.
Certainty, yeah. So yeah, it was more certain, but it was like less. Couldn't see. It was like near zero. So it was like this challenge where if you want to go to Wisconsin, or you can put more money on Georgia, and so they decided to go with Georgia because of this
In 2020.
Yeah, in 2020, and they won Georgia in that election.
Yes.
Yeah. So for my take about the discussion, I think that it was incredible how she managed to talk about this and show us that all these posterior distributions.
And using simulations of the elections. So
Yeah.
they have a extraordinarily specific utility function.
Yeah.
Does Biden get 270 electoral votes or not? 270 is the minimum amount needed to win. So the utility function is not just electoral votes, because getting 400 is no better than getting 271, and getting like 269 is no better than getting 268. So what they're attempting to maximize is the probability of exceeding 270.
Yeah.
And essentially using decision theory to run a political campaign. What question?
Yeah, actually, I kind of had a question because a new set of polling came out showing that the race is a lot more closer in those swing states. So I don't know, this could be a question of either of you. I'm not sure if it was addressed, but when they make those decisions that we should be putting money on X, Y state, does the polling data like really come into play?
I don't know which data they
Yeah, so she was talking about 2020. They might be doing something a little bit different for
Okay.
2024. Didn't really go into detail about what that was for obvious reasons. Maybe sometime in the future we can talk about that. Certainly polling is one aspect of it. Campaigns have access to more information than what is in like a CNN poll. They do their own polling.
Yeah.
They're doing stuff with the list of registered voters.
Mhm.
So they're using a lot of different sources of data.
Okay.
And Obama actually kind of made that famous 2008, looking at like magazine subscriptions and stuff like that, to, identify people who thought might vote for him, etc. So anyway, yeah, I thought that was extraordinarily interesting. So what did Becca study in college?
Something about maps. I don't
Paintings.
Paintings, yeah.
Not particularly quantitative. So where and how did someone like that learn how to do all this decision theory stuff and become the very senior director of the Biden re-election campaign, despite being, I think, like 30-ish?
Cute.
She sat right there and learned it. It's something that can be learned. There's no obstacle, really. But not having enough people who want to learn it. Alright.
And the other thing that I was like thinking about is something that you can communicate, and in a way it's easy to communicate. Why if you know.
You can put up the graphs.
Yeah, and people understand it.
Yeah. I mean, not everybody understands it equally well, but I mean, she's overseeing
No, yeah.
200 people, and they occasionally have to talk with other, probably more than occasionally, probably more like daily. They have to talk to campaign field operatives and stuff like that. So you're gonna need different tools, but as we've been saying this semester, usually a graph is worth way more than 1,000 words. And it depicts your uncertainty, which in a state like Wisconsin can be a lot more, because the state of Wisconsin does not generate very much or very good, clean data.
When did she take this course?
Hmm?
When did she take this course?
2018? Plus or minus 1 year. I don't know. It was before the pandemic, so I don't know.
What's her name?
Becca Siegel, S-I-E.
Already on her
Yeah. Okay, don't DM her. She can't tell you anything about the campaign, but she is a QMSS graduate. Yes.
I talked with another professor from the political analytics department, and he told me that Wisconsin have like a poor data, particularly on partisanship. So I think that is like the main issue with that data.
Yeah, Wisconsin may be a same-day registration state, so you can sign up to vote and/or switch your party like the day of the election without like in New York, you have to declare whether you want to be a Democrat or Republican like several weeks in advance of the November election. So yes, that among a lot of other things, Wisconsin does a particularly poor job. Like the state of Wisconsin does a poor job of producing useful data. All right. So this week, one of the things you'll encounter is, okay, so people think that you should be using different quantitative methods in different situations. That seems like a pluralistic position to take. So if you have a randomized controlled trial like we did with the vaccine thing, then you should be using design-based inference or randomization inference. Fisher, all the same names of the same thing. And if you have a survey with like the General Social Survey or something that is a probability-based sample from a well-defined population, then you should use frequentist methods such as maximum likelihood estimation and talk about the distribution of the estimator across all the different ways that the GSS could have rounded up a couple thousand people to subject to the survey. And if you want to predict the future, particularly if you're in a business context, then you should be using supervised learning because that's what it's geared for. And if you happen to have strong priors, then maybe you should do this Bayesian thing. I can't tell you how many times I've encountered someone who comes up to me and says, well, when I have strong priors, I do Bayesian stuff, and when I don't, I do frequentist stuff. And that makes no sense. You could just do the Bayesian stuff with a weaker prior if that's reflected what you or your audience didn't believe. So Bayesian methods in inference is a belief management system. It's an updating system. When should I change my mind and how much? That should be applicable to all of these situations and more. In particular, Bayesians can generate predictions. We've done this a couple times already on the last couple homeworks, midterm, whatever. So we want to contrast that today with the predictions produced by supervised learning, which is particularly geared toward that method of inference. We want to talk about how those are similar, but mostly talk about how those are different. Because we've spent so much time talking about how Bayesian inference is different from Fisher that we haven't really had time until today to focus on the difference between the Bayesian approach and the supervised learning approach, which is something that is probably more on the forefronts of people's minds today if they're considering Bayesian stuff at all, which they, again, don't really very much in business context, with some exceptions. Insurance is one in which Bayesian thinking, if not Bayesian methodology, has a long history of being used in insurance. You basically have a situation where the expected loss from a hurricane or a car accident or whatever, if you make the expected loss the premium, then that would be like the price you should charge for insurance, making someone indifferent between, paying a $500 premium for sure and having like a car wreck that has an expected damage of $500. But most people who are risk averse would rather lose $500 for sure in a premium rather than having to pay the realization for if their car gets wrecked. So you can be a Bayesian insurance company. Okay, so what is supervised learning? Well, from a Bayesian perspective, supervised learning is like frequentism, except without the probability. That's not how supervised learning people would necessarily describe it, but that's how Bayesians would describe supervised learning. And then the main goal is to predict future outcomes rather than having much caring about interpretation of the model or the parameters thereof. But supervised learning abandons pretty much confidence intervals, p-value, all that null hypothesis testing stuff. They just do optimization to obtain a point estimate, but since they're not doing null hypothesis tests, they are free to change the objective function that they're minimizing or maximizing to be a little bit different. And in particular, they usually add a penalty term, which tends to result in better predictions of the future by doing that. They certainly can relax assumptions like linearity, which may have been important to frequentists in order to derive like the p-values or whatever, if they're not doing p-values in the first place. It essentially requires splitting the observed data that you've collected into some proportion, like 80%, it's known as training, and 20% known as testing. Solve the optimization problem in the training data, possibly further partitioning that training data up into k-folds or using bootstrapping to choose any tuning parameters that may go into the penalty function. And then once you've solved that optimization problem, you've chosen your tuning parameters, then you use the point estimates that you've obtained by solving that optimization problem to create predictions of the outcome in the testing data, and then you can evaluate how well your model procedure is predicting in the testing data, where the testing data, even though it was collected in the past, is sort of intended to be a proxy for future data that is generated by the same data generating process. You will see Bayes' rule sometimes referred to, and you will also sometimes see even a generative model. But I wouldn't say that it's Bayesian because they don't use probability in the estimator. So they're just obtaining point estimates, almost always. Particularly at like the introductory level of supervised learning. But a lot of people who are getting like 250,000 jobs in industry never really get past the introductory level of supervised learning. Yes.
I might be going ahead, but when you're thinking of like naive Bayes classifier, like, you know, when you're working with text and stuff, I know that's one of the common methods. So basically what you're saying is, I know the classifier can sometimes be like it can also be used for unsupervised learning as well. But basically I was just gonna ask, like, is naive Bayes classifier like basically Bayesian or not really?
More naive than Bayesian.
Yeah. I figured, but yeah.
So you're going to maximize or minimize a function in the training data, produce point estimates of any unknown parameters, including doing this business for choosing values of the tuning parameters, and then use those points to predict the outcome of testing data and then evaluate how well you are doing. And this table comes from a paper whose link is there by a number of people, one of whom is named Sarah, and I think her last name is Earp. I always forget what her last name is. Pointing out that the penalty functions that are often used in supervised learning correspond to the logarithm of the kernel of probability distributions that Bayesians can use as prior distributions. But those prior distributions would condition on a tuning parameter, lambda, whose value is generally unknown. So the so-called ridge penalization is proportional to the logarithm of a normal density. So you could use a normal density as a prior, and that is not equivalent but analogous to using ridge penalization. Ridge penalization is not that popular. More popular, lasso or elastic net, which corresponds to this probability distribution that could be used as a prior, known as the Laplace distribution, etc. And then you also get into some stuff like hyperlasso and other things like that that correspond to some other logarithm of a PDF of a prior distribution that Bayesians could use. So just like the past few weeks, we've been doing Bayesian stuff that results in the same log likelihood as frequentists use when they use maximum likelihood. We could, don't have to, we could choose prior distributions that imply the same penalty functions as what supervised learning people use. However, I say analogous rather than the same because the penalty functions being listed here and used a lot in supervised learning don't generally make for very good prior distributions. And that's because if you're thinking about this as just a penalty function in a supervised learning context, then they only matter insofar as how they affect the mode. They shift the mode over and you get to the mode and that's your point estimate. So the penalty functions, they don't matter in the tails. They only matter how they affect the mode. If you're using these PDFs or the logarithms thereof as a prior distribution in the numerator of Bayes' rule, then the biggest influence of those priors is how they affect the tails. And so you can get something with like super heavy, super crazy tails by doing this that gets kind of swept under the rug if you just do this with supervised learning and optimization, because the out tails, they don't matter. It's only the mode. Whereas Bayesian, like I was saying before, you're essentially saying, well, what sort of parameters would be substantively reasonable? And if you put something that has like very heavy tails, then you're putting positive prior probability on stuff that is unreasonable, scientifically. So an example of this with the lasso business, also known as L1 regularization. Here is a generative model that Bayesians could use that would be mostly analogous to that. So let's say continuous outcome, we're going to add a linear predictor with an error term. Error term has got an unknown standard deviation sigma. Bayesians care more about this than supervised learning people do. Going to have our usual linear predictor thing, deviating the predictors from their means, which is also very common in supervised learning, but we'll do that here. Have a normal prior on the intercept. And here's where we're going to do something a little bit different. Before we just said, well, each beta is normal and it can have a mean and whatever. So here we're defining beta sub k to be the negative of lambda divided by sigma, multiplied by the sine of theta, multiplied by the logarithm of 1 minus the absolute value of theta. You might say that's a weird expression, and you would be right. But that is the weird expression that yields something that corresponds to lasso regression. You would need to choose a prior on sigma in addition to a prior on lambda in addition to a prior on sigma. And with this form here, we're going to have uniform prior between -1 and 1 on theta. So the logarithm is always going to be well defined. So this process for fixed lambda and sigma implies a distribution on beta that is known as Laplace and has this PDF, conditional on lambda and sigma. So given those, we yield and then the logarithm of that would be what L1 regularization is. However, actual Bayesians need to choose prior distributions on sigma and lambda. And so the marginal distribution of each beta, marginalizing over lambda and sigma when we do the draws, is not exactly Laplace. It's only conditional on lambda and sigma do we get Laplace. So what would the code for this look like? You know, similar to what we've done before. This is a choice for lambda, but Bayesians can make any prior that's positive for lambda, and then just apply the formulas. Now we have draws on the prior for everything, and then we can go on to make prior predictions. So, not that you should do this, but you could, in which case you would be making essentially the same assumptions, or perhaps a superset of the assumptions that supervised learning people are doing when they do lasso, or very similar thing, elastic net, which is kind of a mixture of ridge and lasso. But supervised learning people are going to take lambda to be some point to be determined by k-fold cross-validation in the training data, or maybe bootstrapping these days, rather than a random variate drawn from a prior distribution. And so essentially supervised learning are only doing from like here up, but fixing lambda to be with some process that depends on the data. So it's not even really prior if you're doing k-fold or bootstrapping or something like that to figure out what single value of lambda to use for then getting the estimates of beta and mu conditional on that value of lambda, as opposed to conditional on a posterior distribution of lambda like Bayesians would do. So here are draws of the marginal distribution of beta. The slashes didn't go far enough, but taking the joint distribution of beta and lambda and sigma and then marginalizing over lambda and sigma, just leaving the draws of beta. So we get something that looks like this, has rather heavy tails, but has large concentration at 0. Conditional on lambda and sigma, it's even starker. And the logarithm of it looks like this. But anyway, it's thought to be maybe a reasonable prior distribution. If you want to say, well, I'm pretty sure it's very close to 0, but it has heavy enough tails so that I'm allowing some prior possibility that it's rather far from 0. So you will see a lot of actual Bayesians who want to have a prior that looks more like this than a normal distribution, which has light tails. Wanting in general more concentration near 0. If it's still got to integrate to 1, so if you have more concentration near 0, then you can compensate that by having heavier tails than a normal distribution. So thinking most coefficients are near 0, but maybe some small subset of them could be rather far away from 0, and wanting to learn that. All right. Okay, so questions about that? So I talked a second ago, okay, here's like a generative process. So when supervised learning people say generative process, again, like frequentists, they're conditioning on points of the parameters and just talking about like generative from here up, not all the way. And they take lambda to be a point rather than a random variable. So how do supervised learning people choose lambda? There's some various ways, but they all kind of amount to conceptually about the same thing. So again, we're splitting our original data into training observation and testing observation, usually about 80% training, 20% testing, something like that. And then further splitting up the training data into k folds, each that has n1 over k rows. And then iterating through steps like this, take a guess of lambda, solve for the optimal values of the other parameters like beta and mu, using k minus 1 of the folds, predict the outcome in the remaining fold, average the loss over observations, do that holding out each of the k folds, etc. Use that to come up with an improved guess for lambda, and then when you go back and forth with this and it doesn't change by very much, then you stop. And you've arrived at a candidate value of lambda that you can then go on and solve for beta, estimates of beta for real, given that value of lambda. And then given those values of beta, you can make predictions for the outcome in the actual testing data and evaluate these loss functions. So one thing to be acutely aware of, well, the loss function that people are using to evaluate the testing data, it usually doesn't have the penalty term included in it because you're already past the point of estimating when you get to predicting the outcome in the testing data. So the loss function can just be a log likelihood function. And in fact, that's pretty much what it is for Bayesians. But supervised learning people have invented many loss functions. And depending on which loss function you choose, that can drastically affect your conclusion as to which model predicts better with respect to whatever the criterion loss function is. And of those many loss functions that supervised learning people cook up every day, a large proportion of them are what are known as improper loss functions, which is in contrast to a proper loss function. A proper loss function has the property that it is maximized by the true values of the parameters. So if somehow you got like the true betas, that would yield the smallest loss if you have a proper loss function. But supervised learning people are rather averse to the idea that you could ever have the true betas. And so if you give up on the idea of even trying to obtain true betas, whatever that even means in a lot of these contexts, then that seems like it would open up the door to use a whole lot of other loss functions potentially that are improper. However, once you open up that door, essentially anything could happen. You know, you choose this loss function, model A is better than model B. You choose this loss function, model B is better than model A with respect to that. And so a lot of your conclusions about which model is better hinge, and hinge is actually one of the loss functions, on what improper loss function you do to the evaluation. So one of them is mean squared error in the testing data. So subtract the prediction from the outcome and square it and then sum it over all into observations in the testing data. That's proportional to a Gaussian log density, ignoring that part. And then you have the sigma squared here. There's just a proportionality constant that's assumed to be known. You'll often see the square root of this, which is known as root mean squared error. But that's a monotonic transformation, and that's not going to change the ordering in which models are ranked. And particularly with binary outcomes, the loss function will usually depend on the elements of the so-called confusion matrix. So classifying the outcome in the testing data is either success or failure, depending on whether the probability implied by the point estimates is greater than 0.5 or not. And so you have these deterministic classifications as success or failure, but they can be wrong. And so you get the so-called false positive rate, false negative rate, all kinds of other functions of the proportion of correct and incorrect classifications. And any loss function that is based on discretizing a continuous thing, like eta, the log odds, or the probability of success, any continuous thing, if you discretize it at 0.5 or whatever, you're automatically going to have an improper loss function. The only proper loss functions are continuous, basically. So you know, if you've seen any supervised learning at all, you've seen a whole bunch of names and a lot of different functions for basically taking 4 elements of the so-called confusion matrix and doing something with them to make a loss function to say, like, how well are we classifying observations in the testing data. And all this sensitivity and specificity and area under the curve and all this comes from that. And in particular, it comes from discretizing the continuous output of the model after having estimated the parameters in the training data into yes or no's. But they're doing it just once per observation because they don't have a whole posterior distribution to make many predictions from and average, anything like that. All right. So for Bayesians, like the most common and well justified utility function for how well we're predicting data, future data, would be the logarithm of the density function or the mass function, depending on whether it's continuous or discrete, of the outcomes. And that, because it's Bayesian, is a proper scoring rule. It will be optimized by the true parameters, assuming that is a well-defined thing. And it's not as if Bayesians are saying, like, well, we obtain the true parameters, but we are trying to obtain the true parameters. And so that motivates Bayesians to use proper loss functions, in particular, the logarithm of the function that you think generated the data, whether that's discrete or continuous, depending on the outcome. So decision theory says you should choose the model that maximizes expected utility. Utility in the Bayesian context for prediction, it makes the most sense to use the logarithm of the PDF or the PMF for the outcome. So if that's our utility function, we have the expected logarithm of the predictive density, even if the outcome is discrete. We just say expected logarithm of predicted density, and we might choose the model that maximizes that. So what would that be? So that's the expectation with respect to future y of the logarithm of the predictive distribution. So the conditional density of the future y's, n plus 1, n plus 2, all the way up to 2n, given the n past y's. Since it's a logarithm, assuming the future values to be conditionally independent of each other, we can write this as a sum of integrals, wherein we do the Bayesian hokey pokey, where we take the density function for a future outcome given the parameters and weight it by the posterior density of the parameters given the past data that we've actually collected, integrating that both over the parameters to get rid of them, and integrating this over the future values that the y can take. So that integral is usually intractable analytically, won't have an elementary solution most of the time, but it can be approximated rather well, particularly if you have a decent amount of data, by the logarithm of the predictive density for the nth observation in the past data, conditional on all but the nth observation in the past data. So we're trying to estimate this, but we're going to use the past data, omitting one observation, conditioning on all the remaining observations, getting that predicted density, the logarithm thereof, summing it up to get an estimate of this, which is resembling what supervised learning people refer to as leave one out cross-validation. Essentially k-fold cross-validation where k is equal to capital F. And so for past data, we can do the Bayesian hokey pokey, or we can do it with draws. So we don't have to wait for the future data to actually arrive. So this y to the negative n, that's the same as in our syntax, indicating all but the nth observation. And there's capital N ways to do this that we could sum this over. Now, it looks like we have to do the Bayesian hokey pokey capital N times, because there are capital N ways to leave out one observation and then condition on the rest. However, this piece here is just the distribution we're assuming for the data, like binomial or Gaussian or whatever. So if we could somehow obtain this piece here, posterior density of the parameters conditional on all but the nth observation, without having to do capital N separate calls to stand. So is there some way that we can get this f of theta given y excluding the nth from the draws of f of theta given all the y's? And that can actually be estimated rather well using only one set of draws of theta, assuming the nth observation doesn't have an outsized influence on the posterior distribution. And that is an assumption that we can verify with the procedure that I'm going to talk about now. So big picture here, we are estimating the expectation of the log predicted density. Log predicted density being our utility function for predictions of future data. But we're not going to wait for the future data to arrive. We're going to estimate this using only past data and essentially leave one out cross-validation. But it would be time-consuming to do leave one out cross-validation literally. So rather, we're going to estimate what would happen if we did do leave one out cross-validation using one set of draws that we obtain once for all the parameters given all the past data. And that requires a slight additional assumption that none of the past data has an overly influential effect on the posterior distribution relative to all the other data points. But that's something that we can check. So let's talk about how we would do that. So this is an example using national election study data. That survey happens after every presidential election. It has an income variable that has integer codes, so I'm going to coerce that to a factor so I get dummy variables rather than assuming the relationship between income and log odds for voting for the Republican candidate is linear. I'm going to chop it up into dummy variables. I'm going to change age from, instead of putting the units in years, I'm going to put it in decades, because 1 year difference is really too small to be anticipating it has much of an effect on anything. Whereas a 10-year difference might actually be big enough to where I can think about what that coefficient would be. All my variables or predictors are discrete, so I'm going to group this to the group level so I can do binomial likelihood rather than Bernoulli likelihood. That implies the same information, same posterior distribution, but it's going to be faster if I group the observations into fewer rows and also make it easier for me to do diagnostics with binomial rather than the individual Bernoullis. Anyway, I'm going to do a logit model. I have some priors. It runs, it's fine. And then I'm going to call the LU function, which is short for leave one out. And it is much shorter than what the actual estimator is, which is Pareto smooth importance sampling, leave one out, cross-validation estimator of the ELPD, which, if you were to acronym, would be PISISLOO ELPD, which is too long to be an acronym. So you just call it the LU function, specifying here save the Pareto smooth importance sampling stuff because we're going to need it later. And that runs. It hinges on the log likelihood. So this model had 365 observations. I have 4,000 draws of the parameters, and I can evaluate the log likelihood contribution for each of my 365 observations in the past data as columns, sort of internally. And it comes back with this, So the leave one out cross validation or Pareto smooth important sampling leave one out cross validation estimator of the ELPD is right here. It's estimated to be negative 362.6. This has essentially no relevance in isolation. It is only useful in comparison to another model, in which case higher values of the expected log predicted density indicates that model is expected to predict future data or give us more expected utility than a model with a lower value. And this is negative, so closer to 0 means better. It doesn't always negative, but a lot of times it is. Then we have Lu IC, which is negative 2 times this. That's all it is. However, Lu IC is in the units that other so-called information criteria, such as the AIC and the DIC and the CAIC and all kinds of other acronyms that end in IC, which are used by some combination of frequentist and supervised learning in some cases to do model selection. So we multiply this by -2 to give something comparable to that. But if you do that, then the model with the smaller IC information criterion is the one that is expected to give more utility. For this, it's the larger one, expected log predicted density. Also here we have an estimate P underscore Lu, the estimate of the effective number of parameters. That is a quantity that is implied by this. And the effective number of parameters, you can think of it as estimate for how a model that had no prior information, but 7.4 parameters, would give you about this same expected predictions as the model you actually estimated with priors on the parameters. Now, in a model like this, this is going to be very similar to the nominal number of parameters because these priors are rather weak. As we get farther along into April in hierarchical models, you will encounter situations in which the number of effective parameters is much smaller than the nominal number of parameters because of the hierarchical prior structure that we're going to develop for those. But that's something that we'll get into as we get into April. But essentially, the difficulty for Stan of estimating this depends on the effective number of parameters, not the nominal number of parameters. And one way you can think about this, okay, say you have a parameter, but you put a really strong prior on it, like just have a tiny amount of variance, like normal with a standard deviation of 0.00001. Not that you should, but imagine that you did. Well, nominally, that would count as one additional unknown. But if you're putting a normal prior with a standard deviation of 0.001 on it, you're saying, I basically know this. It's basically not being estimated. So the effective number of parameters would be one less in that scenario. And then in a hierarchical model, it can be a lot less. So this is a measure of the complexity of the model. It's not something that you need to, it's implied by this. So you don't need to mentally apply a complexity penalty to this because this already reflects that different models could have different amount of complexity as quantified by their effective number of parameters. So we're going to need another model to compare this to, but I would point out this last thing here, all Pareto K estimates are good, which is to say less than 0.5. That reflects the assumption or the verification of the assumption that I referred to earlier, that none of the individual observations has an outsized influence on the posterior distribution. If anyone did, its Pareto K estimate would not be good, and you would get a different message at the bottom saying everything is not okay. Right? But in this case, it was. So we can go on to do model comparison using Pareto smooth important sampling, leave one out, cross-validation estimator of the ELPD, such as changing the link function from logit to propit. we can do that and see which model is expected to yield better predictions of future data. So update that, change the family, change the priors a little bit, scale them up by 1.6. Get Lu for our probit model, save this, and we can call the Lu compare function, which is going to yield us the difference in ELPD, which is relevant in the sense that it is saying the probit model is expected to predict future data slightly better in this case than the logit model, because the ELP difference of the logit model relative to the probit is negative for the logit model. However, the difference here is small relative to the estimated standard error. So the main conclusion is that these are both expected to predict future elections about equally well. But if you had to choose exactly one, it would be a slight argument in favor of choosing the probit one. But you never actually have to choose exactly one. And one of the things that you can do is take a weighted average of these two models, which could have a Pareto smooth importance sampling, leave one out cross-validation estimator of the ELPD that is better than any one of the models in isolation. So we can choose optimal so-called stacking weights on the logit and the probit model, come out with a weight of 0.3 on the logit model and a weight of 0.7 on the probit model. And so choosing exactly one would be equivalent to putting 0 weight on one and 1 weight on the other. But it is actually better to, in this case, do 0.3 and 0.7 weights on the predictions of the two models. That yields something that is expected to predict future data even better than either of those models individually. So you don't have to choose just one. You can do weighted average of the predictions and have Lu model weights choose the weights. Also, Lu model weights is great if you have an annoying co-author who wants to use some like weird model that no one else wants to use. You can just do everybody's preferred model, and the Lu model weights will give like 0.02 weight on the model of the weird co-author, and it doesn't really do any damage, but you can include it in the weighted average of the good models. So very useful functions. Also, we can do posterior predictive checking using the Pareto smooth importance sampling, leave one out cross-validation estimator of the expected log predictive density concept. So we've done a little bit of posterior predictive checking in the past already, which is subject to the slight criticism, actually fairly minor criticism, that we're using the same past data to evaluate the models that we conditioned on to get the posterior distribution of the parameters. However, that slight and mostly overblown criticism can be avoided by using posterior predictive checks that are based on the Pareto smooth importance sampling, leave one out cross-validation estimator of the ELPD. Basically, how well would we predict the nth observation given all the other observations? So rather than using all the same data to get the comparison that we use to condition on to get the posterior distribution. So here's an example using leave one out probability inverse transform overlay. This plot has the property that if your model is so-called well calibrated, then this dark blue line should be basically horizontal, might have a little bit of randomness to it. So in the light blue lines, we've shown contrast. If you just draw from a uniform distribution, you know, the density looks like this. It's not a perfectly horizontal line. But this indicates that our model is predicting too many people who are essentially certain to vote for the Republican candidate in 2000, which was George W. Bush. And it's predicting too few people who have essentially zero chance of voting for George W. Bush in the Al Gore, Florida thing. So this indicates that our model, even the better of the model, the probit ones, is not particularly well calibrated because it's not achieving this uniformity that we hope to achieve. But anything with the LOO in it is going to be using this idea of, well, what if we predict one person given all the other people rather than predicting one person given all the people. But it doesn't make a whole lot of difference, really. So another way in which this comes up, you saw in the McElroy reading today, he goes off on the use of R squared without making it super clear that he's talking about the frequentist R squared, which can be made larger or no smaller by including more and more predictors. So if you just include more and more stuff, you get an R squared closer and closer to 1. But that is essentially a indication of how well you predict the model the outcomes that you conditioned on. And it is a poor estimate of how well you would predict future data, because basically you're including a bunch of noise predictors in there that would not have the same relationship to future data. And this is the thing that supervised learning, with its splitting into training and testing, is intended to avoid. So supervised learning, they care about R squared in the testing data, don't care at all about R squared in the training data. But like I said, McElroy doesn't really make it clear, I don't think, in the reading, that the Bayesian R squared doesn't have necessarily this, well, it can have that property, but we can use the Lu version of R squared. Essentially, what's the R squared predicting a leave one out situation rather than R squared conditioning on the same data that we use to obtain the posterior distribution. And so if we compare the regular Bayes R squared, which is not great, with the Lu R squared, which is conceptually much better, the Lu R squared, particularly in this case, is going to be shifted to the left, to the worst, lower median, lower mean, etc. And that is due to the fact that this is a prediction for held out data, future data, whereas this is predicting the same data that we got the posterior parameters on, and so it's going to be subject to what McElroy is criticizing, whereas this Lu R squared thing is actually not exactly the same, but is more analogous to what frequentists call adjusted R squared, which can go down as you add more predictors to the model. So in a lot of situations, people are more comfortable with the R squared units, even though they're completely arbitrary, as compared to log predictive density. So if you encounter one of those people and are attempting to argue which of your models is expected to predict future data better, you can do it in Lu R squared units rather than log predictive density units, which, like I said, only are meaningful relative to another model, not in any absolute sense. So basically, with all these model checking things, if you can do a leave one out concept, you should. Whatever. So here's a lasso thing. It can be done with the GLMNet package. You give it your X data, you give it your Y outcomes, specify family binomial for a logit model, and it's going to try this with a bunch of different values for lambda that you can give it. And when it does the optimization, depending on the value of lambda, it might make the coefficients on all of these be exactly 0, depending on the value of lambda. And then you can go through this and figure out, well, which value of lambda and its associated coefficients is yielding me the best k-fold or bootstrapping or something like that to choose them. So for higher values of lambda, all the estimated coefficients except for is the voter white are 0. And then for lower values of lambda, then income starts to matter a little bit, etc. And then we can, or they can, figure out what lambda yields the best predictions with k-fold or something like that. So the frequentist, the supervised learning, and the Bayesian procedures give different recommendations as to how to proceed with a model. So what is called or referred to as frequentist is what I refer to as frankenfrequentist, because it takes bits and pieces of Fisher and Neyman and some other people, some Bayesian stuff, throws it all together in this stew that makes no sense, but that's what you see people doing in the literature. And the frankenfrequentist procedure is to proceed as if a coefficient is zero, unless you reject the null hypothesis that it is zero in favor of the alternative hypothesis that it is not zero. And if you do reject the null hypothesis that it is zero, proceed as if the true coefficient is the estimated coefficient, point estimated coefficient. So this makes no sense for a variety of reasons, but it's also very discontinuous. So if your p-value is like 0.06, we're going to proceed as if beta k is 0. If your p-value is 0.04, then we're going to proceed as if it is whatever the maximum likelihood or least squares estimate of that is. And so there's a lot of things that can be criticized about that. It's not really fair to criticize frequentism on these grounds, because that is not even frequentist. It's mistaking realization of a random variable, the point estimate, as if it were a pre-registered hypothesized value, which it is not. It's an open invitation for so-called p-hacking, where you like do some stuff, drop some outliers, whatever, to make the p-value be slightly less than 0.05, so that you don't have to treat it as zero. And p-hacking has been a huge problem at the root of the replication crisis in psychology that we talked about the first day, and generally a bad thing in social science otherwise, and even outside of social science. And this whole frankenfrequentist procedure obviously implies the distribution of published estimates is going to be a biased distribution relative to the distribution of all estimates, published and unpublished, if you have this sort of screen where you have to have the p-value be less than 0.05 in order to publish it. What you're going to see in the published literature is tending to be vast overestimates of what it is, and what doesn't get published are the underestimates. And so if you considered the published and the unpublished estimates all together, they might be an unbiased estimator for the true population thing. But if you just consider the published ones and never see the unpublished ones, then you get estimates that are biased away from zero all the time. And that was something that people should have recognized at the time, and some people did, but those people were ignored, and those people tended to be Bayesians. But anyway, supervised learning has a different procedure, not based on frankenfrequentism. You proceed as if the true beta is the estimated beta, but the estimated beta may be exactly zero if you use a penalty function that is not differentiable at zero, such as L1 regularization. It has a cusp at zero rather than being differentiable at zero, and so it is entirely possible that some of your coefficient estimates given lambda are exactly zero, in which case you just proceed as it is. But if the coefficient is estimated to be exactly zero, that is equivalent to taking it out of the model. You're just multiplying some predictor by zero. That's the same thing as not having the predictor in the first place. And so the supervised learning people say that this is a preferable procedure for choosing what should or should not be in the model, as a way of pruning away predictors that add more noise than they add signal to the predictions. But both of those stand in contrast to the Bayesian procedure, which is you just proceed with your draws to the posterior distribution. If they're near zero, if they're far from zero, they're not hurting anything. They're actually helping. So none of your draws of beta are exactly zero, but they could be closer or farther away from zero. But you just include all of it in your predictions. And that yields the best predictions, assuming the correct model. So you can just proceed with that. Okay, so I had a plot here that got Eaton. Do I have enough time to make my plot? Let's send that. 3 minutes.
Okay.
Lost a couple at the beginning. Questions about model comparison, the different procedures, Perez with important sampling, leave one out, cross validation estimator of the ELPD. Any of that? Come on. All right, so actually in my last couple of minutes, I'm going to skip one thing, couple things, and talk about this. So supervised learning is closely associated with data science, although data science might be a broader thing than including most of supervised learning as a part of it, but not all of it. And what you often see with supervised learning is one of these Venn diagrams. This is done by one of the people named Conway, but you'll see similar diagrams all the way where data science is the intersection of like substantive expertise and math and statistics knowledge and, you know, computer manipulation skills, which is referred to as hacking. That's not intended to be pejorative, but anyway. And you get machine learning or supervised learning kind of up here where, you know, involving these algorithms and some math, but limited, if maybe none, substantive knowledge or even interpretability. And so what I want to mention is, or point out, well, what happens if we specifically equate math and statistics knowledge with probability? Like that's, math is broader than all that, but let's say we're just saying the green stuff is knowledge of probability. And then the blue stuff would be enough to have substantive expertise in order to specify priors on the parameters and build a generative model for like veto overrides or whatever. And if we associate specifically the red stuff, algorithms, with Markov chain Monte Carlo, then the intersection of those three things would be what? Bayesian. So Bayesian estimation, Bayesian inference has been what data science purports, or at least what Conway purports data science to be since at least 1990 when Markov chain Monte Carlo was introduced to Bayesians in that Journal of American Statistical Association article. And, you know, if we'd had the MCMC, we would have been at the intersection of all this even going back centuries. But what is under the umbrella of data science today mostly is not Bayesian. It is definitely on the border here, maybe even north of the border here, in like the Canada of the Venn diagram, where, or maybe even, you know, Alberta or something like that, where we have a lot of emphasis on computer hacking sort of stuff, not so much on substantive expertise. And it's gotten to where you don't even really need to know the math underlying your convoluted neural net or whatever in order to make predictions from your convoluted neural net, which are convoluted predictions. So what I would argue is that Bayesian estimation, Bayesian inference is what data science was originally purported to be, but not what data science currently as practiced is. Data science as we know it today largely came along 10, 20 years later, but instead of building on modern Bayesian inference with MCMC, went in its own direction. And I gave a link up at the top here to a webpage that you can go to get a ticket, only costs $20, to Data Science Day at Columbia University. So you can pay $20 to go to something that you've already paid $75,000 to attend, to see presentations, posters, and a whole bunch of invited talks done by this all-day conference put on by the Data Science Institute at Columbia University, which was formed in 2015, 2016, something like that, has a master's program similar to QMSS, but not as much social science emphasis. Any event, if you look at the program for Data Science Day, which I believe is next Friday, Thursday, whatever, how many of those presentations that have been invited do you think involve Bayesian inference of the sort of stuff that we've been talking about this semester? Not a damn one. So, what is it that data science is doing that it's strayed away from this diagram, even though they'll still contend that it's the intersection of a whole bunch of stuff that can't be adequately handled by like any one subfield, etc. All right. Questions? We're a bit over time already, so go to whatever the next QMSS talk is. We'll have office hours recitation again next week. We can review more about this model comparison, model checking, model averaging.